In the early stage of my mathematics education, my math classes largely focused on computational skills, whether I could multiply numbers correctly or solve for x an equation, stuff like that. My teachers would tell us that when we add two odd numbers, we would always get an even number, and that the angles of any triangle will always add up to 180 degrees. But we were never expected to know why these facts are true, as is the case for young students all around the world. Enter high school level geometry. For me and for many students, at least in the United States, this is the first class that went beyond the simple acceptance of mathematical facts and introduced the concept of showing why such facts are true. But for many students, including myself at the time, the notion of proving anything mathematical seemed daunting. Now, as a college mathematics student, I have a deeper understanding of proofs than I used to, and I'd like to take you along as I give a brief introduction to some of the basic tools of mathematical reasoning. Let's start with an example. Take an odd number and list out all of its divisors that aren't itself. These are its proper divisors. If you add all of those proper divisors together, we get the aliquot sum of our original number. Now, is it true that the aliquot sum of any odd number is less than the original number? Let's try 3 examples to illustrate what I mean. 9, 35, and 99. First, the proper divisors of 9 are 1 and 3. Add them together, and you get 4. 4 is less than 9, so that's one supporting example so far. Next, the proper divisors of 35 are 1, 5, and 7, which add up to 13. 13 is also less than 35, giving us a second supporting example. For 99, we have the proper divisors 1, 3, 9, 11, and 33, giving us an aliquot sum of 57, which is once again less than our original number 99. From our 3 test cases, we haven't found any counterexamples to our claim. In fact, if we check all of the first 450 odd numbers, they are all greater than their aliquot sums, meaning we have at least 450 cases where the pattern holds. What we've done here is use observations and patterns as evidence to try to evaluate a claim. This technique has a name: inductive reasoning. But now, here's the million-dollar question. We have 450 supporting examples for our pattern, but does that prove that the aliquot sum of an odd number is always greater than the number you start with? Think about it this way. Despite having confirmed that the pattern holds for the first 450 odd numbers, we can't conclude from this that it will continue to work for any of the odd numbers we haven't checked yet. In fact, check out the number 945. Here are all of its proper divisors. They add up to 975, which is greater than 945. And just like that, we have a counterexample. The key is that there's no way of being certain that cases we haven't checked aren't counterexamples to the pattern, meaning checking several examples and generalizing a pattern isn't sufficient to make a valid proof. It turns out that inductive reasoning alone isn't enough to prove a statement with absolute certainty. So if finding a pattern doesn't always work, then we will need a different type of reasoning. To illustrate this, I'd like to go back to a problem at the start. How do we know that the sum of 2 odd numbers is always even? Perhaps it may seem really simple, but to start, we can think about what makes a number odd. An integer is even if it can be evenly divided by 2. And an integer is odd if it can't be evenly divided by 2. And in particular, there will be a remainder of 1. For this reason, you can define an odd number as an integer n where there exists another integer k such that n equals 2k plus 1. So now we have a definition of an odd number. What next? Let's see what happens when we add 2 arbitrary odd numbers, m and n. Using our definition of odd, we can say m equals 2k plus 1 and n equals 2l plus 1, where k and l are both integers. When we add m and n together, we get 2k plus 2l plus 2. Let's do some algebraic manipulation by factoring out a 2, giving us m plus n equals 2 times the quantity of k plus l plus 1. The sum of m and n is equal to 2 times an integer, so m is even. To recap, we took two arbitrary odd numbers and showed that the sum is even using a valid logical argument called a proof. This technique of using logical arguments also has a name, not inductive reasoning, but deductive reasoning. Unlike the generalization we made with the previous problem, proofs allow us to be not just confident that a claim is probable, but certain about whether a claim is true or false. This is because with deductive reasoning, we account for all cases of our statement. In our example, we did that by assuming m and n were any two arbitrary odd numbers. Meanwhile, with inductive reasoning, the point is to make an educated guess of sorts as to if a pattern which exists in some cases extends to other unchecked cases, which, as we already covered, won't always be the case. As I said at the top of the video, at least in my experience, proofs were only introduced in high school level geometry. With that in mind, let's return to the other problem I posed at the start of the video. Why do the angles of any given triangle always add to 180 degrees? We'll start with a triangle. Just like we started with any two arbitrary odd numbers to show that their sum is even, this triangle can be any arbitrary triangle we choose. We'll label the three vertices of the triangle A, B, and C, and the sizes of the angles at each vertex, alpha, beta, and gamma, respectively. Next, pick any of the three edges, let's say AB, and draw a line parallel to AB which intersects the remaining vertex, C. Let's place 2 points, D and E, on this new line, D being closer to A and E being closer to B. Now, take a look at angles BAC and DCA. I claim that these angles have to be congruent. Why? If they aren't congruent, then these two lines wouldn't be parallel, which is to say, they would eventually meet at some point if they were extended infinitely long. So, the size of angle DCA is the same as the size of BAC, which is to say that the size of angle DCA is alpha. Shifting our focus to angles ABC and ECB, using the same logic as before, we know that the two angles are congruent because the two segments AB and CE are parallel. So, angle ECB has the same size as angle ABC, or beta. Now, we have these three angles which have the sizes alpha, beta, and gamma. And furthermore, notice how these three angles, when put together, have a total size of 180 degrees. So, the sum alpha plus beta plus gamma is 180 degrees. Remember that alpha, beta, and gamma are also the sizes of the three angles of our triangle as well. Therefore, the sum of the angles of our triangle, and any arbitrary triangle for that matter, is 180 degrees. And just like that, we have our proof. So we've talked about two different types of reasoning, inductive and deductive. The way I've been talking about inductive reasoning, though, not being sufficient for proving theorems, might make it seem useless. Why use inductive reasoning if we can't prove anything with it? To answer this question, here's one final problem. Consider the first handful of even numbers greater than 2. I claim that these are all able to be expressed as the sum of two prime numbers. For example, 4 is 2 plus 2, 18 is 5 plus 13, 30 is 7 plus 23. You get the idea. Here are the rest expanded. Using inductive reasoning, we might guess that all even numbers greater than 2 could be expressed this way. Greater than 2 because 2 itself can't be expressed as the sum of two primes. But is that the case? The claim itself isn't all that complex. But if you can believe it, we actually don't have a proof of this statement at time of recording. Yet this is a really well-known problem in the number theory world. It's called Goldbach's conjecture. A conjecture, by the way, is a mathematical claim which we believe is true, but hasn't yet been proven. With the help of computers, we know that the claim holds for all even numbers less than 4 times 10 to the 18, again, except for 2. And that's a lot of even numbers, but remember, this is not enough to prove Goldbach's conjecture, because we have no idea if there are any counterexamples greater than 4 times 10 to the 18 that exist. Nevertheless, there's been a lot of work trying to get closer to proving or disproving Goldbach's conjecture. For example, in 2013, a mathematician named Harold Helfgott released his proof of a related conjecture called Goldbach's weak conjecture, which states that all odd numbers greater than 5 can be written as the sum of 3 primes, and his proof is currently in the review process. Another example is that mathematicians have also found formulas which approximate the number of ways to write each even number as the sum of 2 primes. The point is that even though inductive reasoning can't prove statements, it can give us an idea of what mathematical patterns are interesting or seemingly true, and thus worth studying, as was the case with Goldbach's conjecture, and indeed many other conjectures. This video is my entry to the 4th Summer of Math Exposition contest, where I, along with a bunch of other people on the internet, create mathematics explainer content for all of you. When I was looking for a topic to make a video about, I ended up choosing this because proofs are really different from what students are used to in their math classes. If you are one of those students, I hope this video has been helpful. One final note about mathematical reasoning. I talked about everything in this video in the context of math, but it's important to know that these skills can be applied throughout your whole life. You encounter people making arguments every day, and not every argument you hear will logically make sense. People will often make mistakes in their reasoning called fallacies, and sometimes they commit fallacies intentionally if they think it'll make them appear more persuasive. For this reason, it's really useful to be able to tell when an argument is valid. For example, in the world of politics, people aren't always going to use sound arguments to persuade you to vote for them. If you want to make an informed vote, having good reasoning skills to be able to untangle politicians' arguments is a really handy tool. And with that, that's all I have for today. This is the first math video I've ever made, and I hope this isn't the last. So if you have any feedback, leave it in the comments if inclined. Thanks for watching.